We are Group 2, and our final year project title is Hemodynamic Analysis of Blood Circulatory System from Wearable Sensor Data. In the current context, pulse-related readings are only used for basic measurements such as SpO2 levels and blood oxygen levels. Since pulse measurements are closely related to the blood circulatory system, these measurements should be able to characterize the human physiological state. In this project, our main focus was on blood pressure measurement. To achieve our objective, the following 3 deliverables were completed: designing and manufacturing a medical device for multi-channel pulse acquisition, blood pressure estimation using PPG, physiological modeling of the radial artery PPG, medical device for multi-channel pulse acquisition. This deliverable consists of hardware for a multi-channel PPG acquisition device, a mobile application to capture PPG signals, and scalable, secure cloud infrastructure. The custom-made wristband captures PPG signals from the wrist and sends them to the desktop unit. It then sends the signals to the user's mobile application via Bluetooth Low Energy. Once the PPG signals of a patient are captured through the mobile phone, they are saved in an AWS DynamoDB storage. Following are our main and sensor PCBs. The sensor PCB consists of 3 sensor modules, each containing an analog front end, photodiodes, and an LED. The main PCB consists of a microcontroller and a Bluetooth module, powered by a 7.4-volt lithium-ion battery. The device can be charged via USB 2.0. To create the flexible wristband, we came up with our own core and cavity mold design. We have used platinum-cured silicon as the material due to its superior properties. Following is a demonstration of the signal capturing process. The wristband is securely placed above the radial artery of the subject. During the capture, 3 waveforms are displayed on the app screen. Blood pressure estimation using PPG. This deliverable consists of machine learning for blood pressure estimation using single-channel PPG and model interpretability analysis using Shapley values. The machine learning model is based on single-channel input-output U-net architecture. 2 varieties of models are created using cross-attention-based skip connections and FFT-based skip connections. The cross-attention-based model has a quadratic computation complexity, and the FFT-based model has linear arithmetic computational complexity in terms of the number of samples. The machine learning models consist of 2 stages. The first stage is the PPG waveform to artery blood pressure waveform mapping. The second stage is the artery blood pressure waveform to systolic blood pressure and diastolic blood pressure conversion. Based on these results, the cross-attention-based model gave higher accuracy but has high compute time. The FFT-based model has less accuracy compared to cross-attention-based models, but results in a reduced compute time. The following diagrams indicate the reconstructed blood pressure waveform against the actual blood pressure waveform. The prediction follows the actual waveform pattern. Interpretability is significant when it comes to diagnostic machine learning models. We carried out an interpretability analysis of stage 1 of our machine learning model with SBP and DBP fine-tuning. Systole and diastole of the artery blood pressure correspond to related sections of the PPG waveform based on Shapley values. This indicates that our machine learning model is interpretable against SBP and DBP with respective to input PPG waveform. Physiological modeling of the radial artery for PPG. When modeling a PPG signal, we can recognize it as the result of 3 main mechanisms occurring sequentially. First, the heart initiates a pulse wave in the arterial network. Then, this pulse wave propagates through the arterial network up to the point of acquisition. Finally, during PPG signal acquisition, light is reflected to capture the signal. To model these 3 components, we have developed a physiological model. To simulate cardiac behavior, we used a parameterized cardiac output waveform. For pulse wave propagation across the arterial network, we employed a 1D mathematical model. Using the variations in blood pressure, flow velocity, and cross-sectional area from the blood flow simulation, we simulated light propagation according to the Beer-Lambert law to calculate the PPG signal. Following is a demonstration of the physiological model that we have developed using Python. In this slide, you can see the output of each section and the final PPG waveform output. During a final year project, we delivered medical device for multi-channel pulse acquisition, machine learning model for blood pressure estimation using PPG, physiological model for radial artery PPG. Thank you.